So for our first one here, we got v equals x cubed. We're finding the derivative with respect to time. So that's going to be dv over dt equals, and then for the x cubed, remember you are using chain rule here. So it's going to be 3x squared as normal, but then times the derivative of the inside. So that's dx over dt. That's the derivative with respect to time. Therefore, we're done. That's all you got to do there. The next one. This is a surface area equation, so SA is actually a single variable in this case. I find the derivative with respect to time just like I did the last one, so it's going to be dSA over dt equals, so we're going to do 4 pi times the 2, I'll go ahead and call that an 8 pi now, times r. But, of course, we're finding the derivative with respect to time, so use chain rule on the r, so it's times dr over dt. And then that one's done as well. So we know that we're dealing with a circle, and the circle is growing here. And we know it's growing at 60 centimeters per second. We want to know the rate at which the area, notice, within the circle is increasing after t seconds. Now, what I glean from all that information is that I need to be starting with area of a circle. And so an equation isn't given here. You have to know that equation. In order to calculate the area of a circle, you end up doing A equals pi r squared. How do I know to use that? Because that's the equation for area of a circle. Now that we have an equation, you want to know what's happening at t seconds. So that tells you find the derivative with respect to t. So dA over dt equals 2 pi r dr over dt. Now, plug in what you know already. Alright, so as we now go through and we start plugging in what we already know, first of all, notice what we're looking for. We want to know the rate at which the area is increasing. So that tells me that dA over dt is what I'm going to be solving for. So it's going to be dA over dt equals still, equals 2 pi. Of course, 2 pi stays the same. And then since I'm solving for d over dt, I'm going to have to know what r is, and I'm going to have to know what dr over dt is. Now I got the 60.
Oh.
Notice the 60 is 60 centimeters per second. So I actually know that must be the rate at which the radius is changing over time. But what is r?
Nobody knows.
Well, we don't know the radius at this exact moment. But it does say after t. So when you're faced with this kind of situation, we can now tweak our process just a little bit. We can add one more thing in. I want to write an equation for the radius so that I can plug it in there. Now, how would you describe the radius in terms of time for this situation? Well, at 0 seconds, we would say that the radius is 0. We can go ahead and go from there. After 1 second, what would the radius be?
What?
60, yeah. After 2 seconds, what would be the radius?
120.
120, because remember, it's increasing by 60 centimeters a second. So, notice you were doing 60 times the number of seconds, so you got a 60t. So we can then plug that 60t in for our radius. So every now and then, we can actually calculate it, but you can also write its own little equation like that about what you would have done. So from there, it's a matter of just cleaning up, doing the little bit of math that we have left at this. And so we end up with 60 times 60, which is 3,600. Double that, that's 7,200 pi t. And so what this tells us is that you can now take whatever t is and plug it in and find out how quickly the area is increasing. Now notice the area is increasing very, very fast. Because if the radius is changing by 60 centimeters per second, it's actually going pretty quick there. But 60 becomes 7,200 pi by the time you look at area, because of course the area equation is pi r squared. So every little bit the radius increases, the area is increasing far more than that as well. When looking at a problem like this, especially a brand new type. Like this is the first type where we got a ladder leaning against the wall. You'll see the same kind of setup come back again in the future. But when you haven't dealt with one before, unless you instinctively know what equation you should be using, I would always suggest drawing a picture. It really helps you to remember where everything goes. And so this is the picture in this case. You'll notice I've got my wall going vertically, and then we got the ground horizontally. I drew the ladder in, which is of course slanted. And then I want to remind myself what is moving where. And so notice the bottom of the ladder is sliding away from the wall. So I got a little arrow down there to remind myself of what is moving where. Now, I want to go ahead and start labeling that picture. So the first number I have in my problem is the 10 feet. So that 10 feet has to go somewhere. Now, it's the ladder. So that, of course, is whatever's leaning against the wall. So that's my 10 feet right there. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. So that's how fast that arrow is moving. That's 1 foot per second down there. And then how fast is the top of the ladder sliding down the wall? Okay, that's what we'll look for. I'll actually make note of that by showing this is what I'm trying to figure out. And then when the bottom of the ladder is 6 feet from the wall. Okay, so I know that this distance here is going to be 6 feet. And I got kind of an affinity for this way of measuring and labeling my diagrams. So I tend to actually put the little lines there to show it's between this point and this point that's 6 feet, so I don't forget about that. But of course, just make sure that it is clear to you what the 6 feet really represents. You don't have to do that with the extra lines and all that. All right, so some of you have already seen this, I know, which is excellent. What, geometrically speaking, are we really working with here?
Feet.
It's a triangle, right?
Oh.
Close, close, close.
What type of triangle, to be more specific?
A right triangle.
It's a right triangle. Whenever you see one of these problems where you have a building and the ground involved, we're going to always assume that the ground is horizontal and the building is vertical. Now, of course, that's not actual reality in every single situation, but it at least allows us to be able to work with it without having to get into a whole bunch of trigonometry and stuff like that. So unless you're told otherwise, yes, we can assume that on these. All right, so I know it's a right triangle. I got a whole bunch of side lengths involved in this right triangle. What equation do we normally use to deal with sides of a right triangle?
Side, angle, side.
It's the Pythagorean Theorem.
No way.
And so we're going to go ahead and use Pythagorean Theorem in this situation because you'll notice a lot of the work we've done up to this point, it was without an equation. That's because we were trying to figure out what the equation would be that would accurately represent the situation. Once we know the equation, then we actually can do the math part. But we got to get the equation first. Now, one thing before I start doing the math. A lot of times what I'll see people do is try to plug in numbers too early. Where somebody will give this, and then they'll start plugging in some values. And they might end up with an equation that looks like a squared plus 36 equals 100. And then they'll take the derivative.
Wait, what?
And you end up with this thing that looks like it always equals 0 or constant or something like that when it doesn't. So always wait to actually plug in numbers until after taking the derivative when the derivative is required. Now in this case the derivative is required because I have some rates of change with respect to t here. Notice I have a rate of feet per second. That tells me I need to do the derivative with respect to time. Anytime you see that kind of unit, you know you're going to have to do derivative with respect to time. So let's do that. Find the derivative, please, of a squared plus b squared equals c squared with respect to time. All right, now we got our derivative. Now I want to go ahead and start plugging in what I know and then what I need to know. Now, I got the 2's, of course. Now, some of you might be wondering, can I just divide everything on both sides by 2? Yes, you could. I'm not going to because I don't want people wondering what happened to them. But if you see that, go ahead. So I'm going to do 2 times a. Now, right now, I got to make a choice. A could be this side or A could be this side. It can't be the hypotenuse, of course, but it could be either of those. I need to just make a choice arbitrarily here because it doesn't matter which one's which. So I'm going to call A the vertical side. All right, so do I know what A is?
No.
No. Okay, so I'm going to leave that blank for the moment. Okay, do I know what dA over dt is then? No, because notice here, I'm looking to see how fast A is changing, and that's saying that's what I'm trying to find out. So that's going to stay dA over dt. The one that I'm actually trying to find, you go ahead and leave the variables there. Notice I left a blank for the other one, because I'm going to have to come back to that in a minute. All right, next up, the b's. So 2 times b. Do I know what b is?
6.
Yeah, because it's got to be the other leg. So yes, it's 6. And then dB over dt. Do I know what that is?
T.
That is how fast b is changing.
T.
So yes, that is 1. Because b is changing by 1 foot per second. Remember, the bottom is sliding out at 1 foot per second.
We do know what C is.
And then equals 2 times c. Well, c is our hypotenuse, of course. That is our ladder length, which is 10. So we do 2 times 10 times dc over dt. Do you know what dc over dt is?
0.
Yes, good. A lot of people have trouble with that one. It's 0.
So what's my writing?
Because
It's not changing.
dc over dt is how fast is length c changing. Length c is the ladder. The ladder is 10 feet long throughout the whole problem. So it is 0. Now, I got one thing left to deal with here though. Because remember that when I did this, I don't know what A is. And in order to figure out what dA over dt is, I have to know what A is. Can we figure it out?
Yeah, sure, brother.
Yeah. Because of course, we can use the Pythagorean Theorem to find that other side length. So, let's go ahead and do that.
72,
I'm going to end up doing
4, 8.
A squared plus 6 squared equals 10 squared. So A squared plus 36 equals 100. Subtract 36 from both sides. We end up with A squared equals 64. Therefore, A equals 8. That was the hardest part of the whole problem right there. From here, it's easy, right? Go ahead and finish it out. Figure out, what does dA over dt actually equal?
Yeah.
All right.
He looks like Cat
So
Williams.
we do all that work. We end up finding that dA over dt equals negative 3/4. Or in other words, think about what this means again. That means that our value up here, the top of the ladder, is going down by 3/4 what?
Feet per second.
Feet per second. Remember the units when we're actually talking about something real here. And so that then is our final answer. That's what we're looking for here. That the top of the ladder is going down by 3/4 of a foot every second. At that moment at least.
Oh, I know that too.
All right, so once we've figured out our derivative, by the way, I didn't show it up here, but the original equation, a squared plus b squared equals c squared, once again, because it's still Pythagorean Theorem. Found our derivative, plug in everything that we needed to, and then it's just a matter of then solving it for dB over dt, or at least what I called dB over dt. You might have made it the a. It doesn't matter. That's not the important part here. And so we get 7.5, and of course, remember the units. D, and this is also an opportunity to remind you about how we know the units. Remember, for these types of problems, I can say, what is B measured in? It's measured in feet. And then, what is T measured in? It's measured in seconds. Therefore, my rate on this one is feet per second. The same as the dB over dt, and how that stuff gets measured. we know we're dealing with a rectangle, so I drew a picture of the rectangle, labeled some stuff on it that I actually knew in there, and then since I'm dealing with the rectangle area, I knew I need to write an equation for the area of the rectangle, so area equals length times width. Just to be clear here, I'm making this my width, and I'm making this my length. Labeling that is always a good reminder for yourself. Now we need to find our derivative. So, of course, dA over dt. Now I know I'm doing it with respect to time because all this stuff is like per second, which means I got to know a rate that's per second, per time. Now, for finding the derivative of LW, L times W, that's product rule.
Yeah, that's right.
So, I'm going to do original times derivative plus derivative times original. So original times the derivative of W, which is just going to be dW over dt.
W.
Plus
Yep, I messed up on this whole thing.
dl over dt times W. So we end up getting 140 as our final answer there, but of course we need units. Now remember, an easy way to know these units. Look at what we're actually dealing with. What is A measured in? It'd be square centimeters. Yeah, so this is going to be square centimeters per second. Because of course T is measured in seconds here.